With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello everyone, let us start with our question. In this question, what has been asked, draw a schematic diagram of the experiment used by the Davison and Germer to establish the wave nature of the electron. And we also need to explain how briefly how the de Broglie wave relation experimentally verified in case of electron. Now we know that Davison and Germer basically said that we know that electron has a particle nature, so it also proved that electron is also have a dual nature like that of light. Now, for example, let us suppose that this is a electron gun. Okay, this is an electron gun, and there is a high voltage which would be applied here. So this end would be open. Okay, so this end would be open, like from here. This is our electron gun. Okay, electron gun. Now in electron gun, there would be a tungsten which would be here. So inside it, there would be tungsten. Now it would be heated, and then there would be a potential difference which would be applied approximately 54 electron volt of this potential difference would be applied, due to which there would be an electron beam which would be coming. Okay. Now opposite to this, on the other side, we would be having, let's say, nickel plate. Okay, nickel plate. So what will happen? These electrons would be coming here. Okay, they would be striking the nickel plate, and after that they would be basically they would be reflected in different directions. Okay, now we will be having a detector. Let's say here, suppose we are having a detector. Let's say this is a detector on which we will be just observing the intensity. We will be determining where at which angle the intensity would be the maximum intensity. So this is our incident beam IB, and this is our reflected beam. Okay, this is our reflected beam. Let's say this angle supposed to be, this angle is phi. Now at certain value of phi, we observed that there was the intensity of the electron beam was getting to be very much. Now and we should just write that this is our nickel. Okay, nickel. We have chosen the nickel for this case. Now, when the electron comes here, it strikes the nickel, and then we just take a detector. So what we generally thought, we thought that electrons should be scattered randomly. They should not scattered in that they would be scattered in any direction. Okay. But what actually the observation was that we just draw the sketch of the observation. Let's say if we just made a radial curve. So this would be a radial curve in which we would be determining the intensity at different angles. So there would be different angle at which we would be determining the intensity. Now at a particular value of the angle this phi, we get, and this particular value of the voltage, we get this type of a plot like this. That means we would be getting a bump. Okay, this would be just a bump. Now what we can see that if we just draw the line here, so this would be corresponding to angle equals to this phi value. This would correspond to phi value of 50 degrees. Okay, so this is a radial graph. Okay, so that means at this point we need to go like this. Okay, so at phi equals to 50 degree, we would be getting a maximum intensity. Okay, now below this 50 degree, the intensity magnitude would be somewhat less. Okay, and after 50 also, the magnitude of intensity would be somewhat less. But exactly at the 50 degree, so intensity magnitude would be less, and correspondingly the potential difference was 54 electron volt. Okay, that means we are getting a maxima for this condition at a particular angle. So how is that happening? And at some location we would be getting minima and then maxima. So that means that electron beam which is coming here, they would be interacting with the electron, because on the nickel itself there would be electron which would be present. If we just draw this, let's say this is our Bragg plane, and if we just draw certain Bragg plane, so what will happen? So this electron beam would be this interacting with the nickel, and then there would be a interference between the electron here and electron here. Then there would be a interference pattern which would be formed. So there would be a higher intensity, and then there would be we can say that lower intensity, or we can say that constructive and destructive interference. Now this proved the de Broglie hypothesis, which said that lambda for an electron is given as to be h divided by mv. Okay, this is how de Broglie give the value. Now this h divided by mv means the we can say that momentum. Now we can write this because momentum could be related with the potential energy and the kinetic energy. Now finally the expression, we know that it turns out to be 2m ev in the square root. This is how the value of the lambda turns out to be. Now if you put the value of the Planck constant, mass of the electron, charge on the electron, then we can say that lambda in terms of angstrom, this turns out to be 12.27 12.27 divided by square root of potential in angstrom. This would be the value. Now if you put the value of this lambda into this expression, if you put the this voltage into this expression, so lambda would turn out to be 12.27 divided by square root of 54. If you put this value, Okay, so this would turn out to be 1.67 angstrom. So this is the value which is proposed by de Broglie. Now, whether this value is correct or not, so if we just use our Bragg equation to get the value of the lambda, Bragg equation to get the value of lambda. So Bragg equation say that lambda would be equals to 2d for n equals to 1 for the first order. It would be 2d and then sine theta. Now, what is d? D is the grating space. So grating space for the case of the nickel is 0.91 angstrom. And what is this theta? So theta is the angle of the incident relative to the Bragg plane. That means this would be the angle theta. So if we just extend the draw a line in the direction of the parallel to the Bragg plane, so this would be our this theta. This is not phi, this is our theta. Now the relationship between theta and phi is given as follows. So theta is equals to 180 minus phi divided by 2. Now if we just put the value, so it would be 180 minus phi value we put to be 50 divided by 2. So this theta would turn out to be 65 degree. Now we calculate whether this would match with the de Broglie wavelength or not. Now if we just measure this value, so lambda would turn out to be 2 into 0.91 into sine of 65. So if we just calculate this result also turns out to be 1.65 angstrom. Okay, that means the experimentally getting value of the wavelength closely matches with our de Broglie wavelength, which is suggested by our this de Broglie. That means this value and this value, these are very close, so they could be experimentally verified. Okay, this result is experimentally verified that this electron would also possess dual nature. So hope you understood the solution. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut App today.